Good afternoon, students. Today we will see the last topic in the digestive system, that is digestion and absorption of nutrients. The major foods on which the body lives can be classified as carbohydrates, fats and proteins, and also some quantities of vitamins and minerals. And they generally cannot be absorbed in their natural forms, and they will be useless as nutrients without the preliminary process of digestion taking place. And that preliminary digestion is the hydrolysis of carbohydrates, fats and proteins. So digestion of carbohydrates. So the sucrose, lactose, starches are all the carbohydrates, and other carbohydrates are also present. So sucrose, which is a disaccharide known popularly as cane sugar, and lactose is also a disaccharide found in milk, and starches are the large polysaccharides present in almost all non-animal foods, particularly in potatoes and different types of grains. And other carbohydrates ingested to a slight extent are amylose, glycogen, alcohol, lactic acid, pyruvic acid, pectins and dextrins. So these are all the sources of carbohydrates which we are taking daily. And the digestion of these carbohydrates starts with the saliva. The salivary alpha amylase is also called ptyalin, that is which is secreted from the parotid glands. It hydrolyzes starch into the disaccharide maltose. The food remains in the mouth only a short time. Not more than 5% of all the starches will be hydrolyzed. So it remains in the mouth only a short time, and the percentage of starch digested is not more than 5%, and it sometimes continues in the body and fundus of the stomach for as long as 1 hour before the food becomes mixed with the stomach secretions. So first the digestion starts in the mouth, which is only for a short time, less than 5% digested, and that digestion continues in the stomach for as long as 1 hour. And the salivary amylase activity is blocked by the 40% of starches to the maltose. Pancreatic alpha amylase is more powerful than the salivary alpha amylase in converting or digesting the maltose. Enterocytes lining the villi of small intestine contain 4 enzymes: lactase, sucrase, maltase and alpha dextrinase. These are capable of splitting the disaccharides. So the disaccharides we know are lactose, sucrose, maltose. They are digested to, the first one, lactose to glucose plus galactose, which accounts to 10%, and sucrose to glucose plus fructose, which accounts to 10%, and maltose is digested to glucose plus glucose, which is the highest percentage of digestion of carbohydrates, that is 80%. And the final products of the digestion of carbohydrates are water soluble monosaccharides, which are absorbed easily into the portal blood. So this is a overall picture of digestion of the carbohydrates. The main food source of carbohydrate is starch, which is acted on by the ptyalin or salivary alpha amylase, that is 20 to 40% only. It acts on the starches, and the remaining starch is digested by the pancreatic amylase, that is 50 to 80%. So it converts the maltose and 3 to 9 glucose polymers to the glucose by means of maltase and alpha dextrinase enzymes present on the intestine. And also along with maltose, lactose and sucrose are also converted by the respective enzymes into their singular products. So all these are again giving glucose plus galactose here and glucose plus fructose here. Coming to the digestion of proteins. So the dietary proteins, that is exogenous proteins, are chemically long chains of amino acids bound together by peptide linkages. So the exogenous source of dietary proteins are having high biological value, like meat, fish, eggs, cheese and other milk products. And soya beans, wheat, other types of various types of pulses are also rich source of proteins. And the endogenous source of proteins are the proteins which reach the intestine through various gastrointestinal secretions and which are present in the desquamated epithelial cells of the gut. So these dietary proteins are digested in the stomach by the enzyme pepsin in the presence of HCl. By the action of HCl, it converts pepsinogen to pepsin, which digests the collagen present in the meat. Pepsin only initiates the process of protein digestion, usually providing only 10 to 20% of the total protein digestion, to convert the protein to proteoses, peptones and few polypeptides. And the major proteolytic pancreatic enzymes are the trypsin, chymotrypsin, carboxypeptidase, carboxypolypeptidase and proelastase. So it is important to note in stomach the optimum pH for the action of pepsin is 2.0. So therefore HCl secretion by the stomach is as essential as pepsinogen secretion for the digestion of proteins. And both trypsin and chymotrypsin split protein molecules into small polypeptides. Carboxypolypeptidase then cleaves individual amino acids from carboxyl ends of the polypeptides. Proelastase in turn is converted into elastase, which then digests elastin fibers that partially holds the meat together. Only a small percentage of proteins are digested all the way to their constituent amino acids by the pancreatic juices. Most remain as dipeptides and tripeptides. So it is very much boring subject, but this is very important topic for your examinations, digestion and absorption of nutrients. So the main important points you have to remember: what are all the substances or the sources present for digestion and how they are digested, and the final products of digestion and how these are absorbed. So these few points you have to remember, so listen carefully. So the enterocytes that line the villi of small intestine, mainly in the duodenum and jejunum. These cells have a brush border that consists of hundreds of microvilli projecting from the surface of each cell. That is, it contains the enzyme peptidases. And the amino polypeptidase and dipeptidase convert the larger polypeptides into tripeptides and dipeptides and a few into amino acids. And the dipeptides, tripeptides are easily transported through the microvillar membrane to the interior of the enterocyte by the enzyme peptidase, converting them finally into the amino acids. So these are the final products of the digestion of proteins. So you can see here proteins acted by the pepsin in the stomach, converted to proteoses, peptones, polypeptides, which are again acted upon by the peptidases, that is the small intestinal brush border enzymes like trypsin, chymotrypsin, carboxypeptidase, proelastase, and finally converting into amino acids. So whatever I have shown you in the previous slides, so all that points will be covered in a single flow chart like this. So remember this flow chart and convert them into sentences and try to write. And next, coming to the digestion of fats. Most abundant fats of the diet are the neutral fats, also known as triglycerides, each molecule of which is composed of a glycerol nucleus and 3 fatty acid side chains. The small quantities of phospholipids, cholesterol and cholesterol esters are also present. A small amount of triglycerides is digested in the stomach by lingual lipase, that is secreted by the lingual glands in the mouth and swallowed with the saliva. Less than 10% and generally unimportant. So this digestion which is acted upon by lingual lipase and gastric lipase is very much insignificant and unimportant, and it is less than 10%. The first step in the fat digestion is physically converting or breaking the fat globules into very small sizes so that the water soluble digestive enzymes can act on the globule surfaces. So this process is called emulsification of the fat, and it begins by agitation in the stomach to mix the fat with the products of stomach digestion. Then most of the emulsification occurs in the duodenum under the influence of bile. Large quantities of bile salts as well as the phospholipid lecithin. So this entire digestion and absorption of nutrients topic is present in your biochemistry textbooks also. So read from both the textbooks and you get the concept of the topic, and then you can write easily in the examination. So remember the flow charts, how the source or main product is digested and the final products are getting, and then you can write easily in the sentence formation. So the lipase enzymes are water-soluble compounds and can attack the fat globules only on their surfaces. Enzyme for digestion of the triglycerides is pancreatic lipase. The enterocytes of the small intestine contain enteric lipase. Most of the triglycerides of the diet are split by pancreatic lipase into free fatty acids and two substances of the two structures of the monoglycerides. So these are the final products or the end products of the fat digestion: free fatty acids and monoglycerides. So this picture you can see here, fat under the action of bile plus agitation that will be producing the emulsified fat. So this emulsified fat under the influence of the pancreatic lipase enzyme is converted to the fatty acids and to monoglycerides. So the bile salts, when in high enough concentration present in the water, have the propensity to form micelles, which are small spherical cylindrical globules. So these are 3 to 6 nanometer in diameter, composed of 20 to 40 molecules of bile salt. Inside, the micelle contains inside the fats and outside surface is water soluble. The bile salt micelles also act as a transport medium to carry the monoglycerides and free fatty acids, which are relatively insoluble to the fresh borders of the intestinal epithelial cells. So this is a picture of a micelle. Outside it is, so the central part is free fatty acid and cholesterol, and surrounded by the bile acids. So these are the hydroxyl group, peptide bonds, carboxyl groups, and these are the phospholipids. So bile salts are released back into the chyme and again reused. The enzymes cholesterol ester hydrolyzes the cholesterol ester, and the phospholipids are hydrolyzed by the phospholipase A2. The bile salt micelles play the same role in ferrying free cholesterol and phospholipid molecule that they play in ferrying monoglycerides and free fatty acids. So ferrying means transport of substance from short distance from one point to the other point in a cell. No cholesterol is absorbed without this function of the micelles. So you can see here dietary triglyceride fat acted upon by the pancreatic lipase. So this will be converted into micelles under the action of the bile salts. Fatty acid absorption in presence of bile salts and fatty acid absorption in the absence of bile salts. You can see. So all these are the phospholipids, cholesterol, triglycerides, which are simply coming here, but they are not absorbed. So in presence of bile salts, they are converted to micelles and they will be easily absorbed. So we have seen till now the digestion process of the various carbohydrates, proteins and fats. Now we will see the absorption. Stomach is a poor absorptive area of the GIT because it lacks the typical villus type of absorptive membrane, and also because the junctions between the epithelial cells are tight junctions. Only a few highly lipid soluble substances such as alcohol and some drugs like aspirin can be absorbed in small quantities. Absorptive surface of small intestinal mucosa showing many folds called valvulae convenientes or folds of Kerckring, which increase the surface area of absorptive mucosa about 3-fold. These folds extend circularly most of the way around the intestine and are especially well developed in the duodenum and jejunum. So you can see here the absorptive surface area of the small intestine especially is having the many folds, valves of folds of Kerckring. So these are having the brush borders and the villi, intestinal villi. So while the food is moving like this, so the absorptive surface area is more and all the digested end products will be absorbed from here. The villi lie close to one another in the upper small intestine, but their distribution is less profuse in the distal small intestine. This enhances the total absorptive area 10 folds. Each intestinal epithelial cell on each villus is characterized by a brush border consisting of as many as 1000 microvilli. This increases the surface area exposed to the intestinal materials another 20-fold, total amounting to the 1000-fold increase in the surface area. So this is again one more picture. So you can see here, this is the structure of the villi. This is the arterial supply, this is the venous supply, and the blood capillaries, central lacteal, and the epithelial surface. And this is the cross section. You can see the central lacteal and the brush border having all these epithelial cells. So again, this is one more picture. Immediately beneath the brush border, we have pinocytic vesicles for absorption, and inside the cell, epithelial cell, we have the mitochondria and endoplasmic reticulum, all these things. And coming to the absorption of water, it is mainly by the isoosmotic process of absorption. And the diffusion, which usually the law of osmosis operates, and when the chyme is dilute enough, water is absorbed through the intestinal mucosa into the blood of the villi almost entirely by osmosis. When hyperosmotic solutions are discharged from stomach into the duodenum, water usually will be transferred by osmosis to make the chyme isoosmotic with the plasma. The active transport of sodium requires energy, that is ATP. The intestine must absorb 25 to 35 grams of sodium each day. Whenever significant amounts of intestinal secretions are lost to the exterior, in cases of extreme diarrhea, the sodium reserves of the body can sometimes be depleted to lethal levels within hours. So the chyme contains more sodium than the brush border. So this picture you can see water is simply reabsorbed and sodium also diffuses. So by active transport from the epithelial cells, it enters into the inside of the cell. So 50 milliequivalents per liter. When a person becomes dehydrated, large amounts of aldosterone secreted by the cortices of the adrenal glands causes increased activation of the enzyme and transport mechanism for all aspects of sodium absorption by the intestinal epithelium. This increased sodium absorption in turn causes secondary increase in the absorption of chloride ions and water. Absorption of chloride ions in the duodenum and jejunum. It is rapid and occurs mainly by diffusion. Absorption of sodium ions through the epithelium creates electronegativity in the chyme and electropositivity in the paracellular spaces between the epithelial cells. The chloride ions move along this electrical gradient to follow the sodium ions. Absorption of bicarbonate ions in the duodenum and jejunum. Large quantities of bicarbonate ions must be reabsorbed from the upper small intestine because large amounts of bicarbonate ions have been secreted into the duodenum in both pancreatic secretion and bile. So we have seen in the previous classes there is large amount of bicarbonate in there by pancreatic and bile secretion. So that amount has to be reabsorbed. So it is absorbed in an indirect way. When sodium ions are absorbed, moderate amounts of hydrogen ions are secreted into the lumen of gut in exchange for some of the sodium. The hydrogen ions in turn combine with the bicarbonate ions to form carbonic acid, which then dissociates to form water and carbon dioxide. The water remains as part of the chyme in the intestine, but the carbon dioxide is readily absorbed into the blood and subsequently expired through the lungs. So carbon dioxide here you can see as a byproduct of the digestion and absorption of the nutrients. So secretion of bicarbonate ions in the ileum and large intestine. The epithelial cells on the surface of villi in the ileum as well as on the surfaces of the large intestine have a special capability of secreting bicarbonate ions in exchange for absorption of chloride ions. It provides alkaline bicarbonate ions that neutralize acid products formed by the bacteria in the large intestine. New epithelial cells secrete sodium chloride and water into the intestinal lumen. This secretion in turn is reabsorbed by the older epithelial cells. The toxins of cholera and of some other types of diarrheal bacteria can stimulate the secretion so greatly that this secretion often becomes much greater than can be reabsorbed. Okay, so secretion becomes much greater than what can be reabsorbed. So in cholera toxin, which is acted upon, acted through the cyclic AMP second messenger, causes the opening of chloride channels, causing active sodium pump and in turn leading to the water osmosis. So this is more secretion becomes too much than the reabsorption. So it is causing diarrhea, cholera diarrhea. Calcium ions are actively absorbed into the blood, especially from the duodenum, with the help of parathormones and vitamin D. Iron ions are also actively absorbed from small intestine because the body needs for hemoglobin. Potassium, magnesium, phosphate can also be actively absorbed through the intestinal mucosa. And the monovalent ions sodium, potassium chloride easily absorbed than the divalent ions like calcium. So you can see here in this picture the brush border containing the heme transport protein and the iron transport proteins. So these will be helping in the absorption of heme. Fe3 plus by the help of reductase converted to Fe2 plus ferric. This is ferric, this is ferrous, and this is again reabsorbed in the enterocyte cell along with the proteins, transport proteins, apoferritin and ferritin. So they will be again entering into the blood. Again from ferrous to ferric form it will be converted. Okay, so that will be helping in the formation of the hemoglobin. So now we will see the absorption of nutrients. So first one is carbohydrates, mainly in the form of monosaccharides and small fraction as disaccharides. Glucose is transported by a sodium co-transport mechanism. The first is active transport of sodium ions through the basolateral membranes of the intestinal epithelial cells into the blood, thereby depleting sodium inside the epithelial cells. So second step is decrease of sodium inside the cells causes sodium from the intestinal lumen to move through the brush border of epithelial cells to the cell interior by a process of facilitated diffusion. So first step is sodium coming out of these cells entering into the blood, and second is inside the cell sodium is decreased. So this causes movement of sodium from lumen to the interior of the cell by the facilitated diffusion. Sodium combines with the transport protein, but the transport protein will not transport sodium to the interior of cell until the protein itself also combines with some other substance such as glucose. The low concentration of sodium inside the cell literally drags sodium to the interior of cell along with it glucose at the same time. Once inside the epithelial cell, transport proteins and enzyme causes facilitated diffusion of glucose through the cell's basolateral membrane into the paracellular space and from there into the blood. And the galactose and fructose, galactose is transport is same as glucose, fructose is by facilitated diffusion. So you can see here sodium through the brush border along with it drags the glucose with the help of SGLT, sodium dependent glucose transport protein, into the cell. So this sodium is again taken back into the ECF. So glucose with the help of GLUT2 protein, it will be reabsorbed into the. So absorption of proteins is in the form of dipeptides, tripeptides and free amino acids. The mechanism responsible for the absorption are sodium co-transport mechanism and secondary active transport, and few amino acids are transported via facilitated diffusion. 5 types of transport proteins for transporting amino acids and peptides have been found in the luminal membrane of the intestinal epithelial cells. So this is a small intestinal lumen. This is the interstitial space where you can see through the paracellular pathway water is reabsorbed and sodium along with the glucose it is entering into the cell. So glucose is reabsorbed and here the tight junctions are present, you can see. So sodium along with them, amino acids are also taken back into the cell. So the sodium will again through the active transport it is reabsorbed. So this is the transcellular, this is a paracellular pathway. So sodium it carries along with it glucose and also amino acids. This is the facilitated diffusion. So the micelles perform a ferrying function that is highly important for fat absorption. So I have told you the micelles perform the ferrying function, that is transport from one place to other that is within a short distance. In presence of an abundance of bile micellis, about 97% of fat is absorbed. In the absence of bile micellis, only 40 to 50% can be absorbed. After entering the epithelial cell, the fatty acids and monoglycerides are taken up by the cell's smooth endoplasmic reticulum. They are mainly used to form new triglycerides that are subsequently released in the form of chylomicrons to the base of epithelial cell. They flow upward through the thoracic lymph duct and empty into the circulating blood. Short and medium chain fatty acids, which are more water soluble, are absorbed directly into the portal blood. Absorption in large intestine. About 1500 milliliters of chyme normally pass through the ileocecal valve into the large intestine each day. Most of the water and electrolytes in this chyme are absorbed in the colon, usually leaving less than 100 milliliters of fluid to be excreted in the feces. Proximal half of the colon is called absorbing colon and distal colon is storage colon. So the active absorption of sodium occurs by the electrical potential gradient created by the absorption of sodium causes chloride absorption. Tight junctions present between the epithelial cells of the large intestinal epithelium prevents significant amount of back diffusion of ions. They absorb sodium ions more completely by the help of the aldosterone action. So secretion of bicarbonate causes absorption of the chloride ions. So in the large intestine, finally water is mainly reabsorbed and leaving the undigested products, that is called the feces, so which contains 3/4 water and 1/4 solid, 30% of dead bacteria, 10 to 20% fat and 10 to 20% inorganic matter, 2 to 3% protein, 30% of undigested fiber from the food, bile, pigment and sloughed epithelial cells. And the color of the feces is due to stercobilin and urine. And lastly, we see the applied aspect of the today's topic, that is malabsorption syndrome. So it is a state arising from the abnormality in absorption of food nutrients across the GI tract. Impairment can be of single or multiple nutrients depending on the abnormality. This may lead to malnutrition of the individual and variety of anemias. So it constitutes the pathological interference with the normal physiological sequence of the body, such as digestion, which is intraluminal process, absorption, which is a mucosal process, and transport of nutrients. The causes of malabsorption are the digestive failure caused by the enzyme deficiencies and structural defects, mucosal abnormalities, infective agents and systemic diseases affecting the GI tract. First one, due to digestive failure, like in pancreatic insufficiency, cystic fibrosis, chronic pancreatitis and carcinoma, and bile salt insufficiency by obstructive jaundice and bacteria. And due to the structural diseases, the most common is Crohn's disease because of the defect in the structure of the intestine. And gastrectomy and gastrojejunostomy, fistulae, diverticulae and strictures, infiltrative conditions such as amyloidosis, lymphoma, short bowel syndrome, and eosinophilic gastroenteropathy. And due to mucosal abnormality, again here it is celiac disease. And due to enzyme deficiency, lactase deficiency causing lactose intolerance, and disaccharidase, enteropeptidase deficiency. And due to infective agents, it causes Whipple's disease and intestinal TB, tropical sprue, and parasites. And due to other systemic diseases, the hypothyroidism and hyperthyroidism, and diabetes mellitus, hyperpara and hypoparathyroidism, carcinoid syndrome, and malnutrition. Coming to the symptoms of this malabsorption syndrome, this can be extraintestinal and intraintestinal. Diarrhea, often steatorrhea, is the most common feature. It is due to impaired water, carbohydrate and electrolyte absorption. Other symptoms include weight loss, growth retardation, swelling or edema, anemias, muscle cramps and bleeding tendencies. Specific disease entities causing malabsorption. We will see some of the important. So the first one is celiac sprue. It is a common cause of malabsorption. So it affects the age ranging from first year of life through the 8th decade. And the etiology is exactly not known, but 3 factors can contribute, like environmental, immunological and genetic factors. So there is association of the disease with gliadin, a component of gluten that is present in wheat. And immunological factors like serum antibodies are detected, such as anti-gliadin, and genetically almost all patients express the HLA-DQ2 allele. And it is diagnosed by a small intestinal biopsy, which should be done for suspected patients. A hallmark of the disease is presence of abnormal small intestinal biopsy. And the next entity is the tropical sprue. It is caused by the infectious agent including Giardia lamblia, Yersinia, Clostridium difficile. It tends to involve the distal small bowel. There is total villus atrophy, which is not uncommon, and the Crohn's disease is an inflammatory bowel disease marked by patchy areas of inflammation anywhere in GIT from mouth to anus. It attacks the body. The body's immune system attacks the GIT, leading to the chronic inflammation, so which is the most common reason of inflammation in the GIT. And the next entity is short bowel syndrome. So following resection or diarrhea and or steatorrhea, it can appear due to decrease in the area of absorptive surface area. And the other symptoms include cramping, bloating, and heartburn. In the bacterial overgrowth syndrome, there is a proliferation of colonic type of bacteria within the small intestine due to stasis caused by the impaired peristalsis. This leads to diarrhea and malabsorption. And the pathophysiology of this bacterial overgrowth syndrome, bacteria overgrowth occurs leads to metabolizing the bile salt, resulting in deconjugation of bile salt, that is decreased bile salt, and malabsorption of fat occurs. And the damage of intestinal villi occurs by bacterial invasion, toxins, and metabolic products. Damaged villi causes total villus atrophy. So finally, the management of malabsorption. So we have to replace the nutrients, electrolytes, and fluids, and in severe deficiency, hospital admission may be required for parenteral administration. Pancreatic enzymes are supplemented orally in pancreatic insufficiency. Dietary modification is important in some conditions, that is gluten-free diet in celiac disease, lactose avoidance in lactose intolerance. Antibiotic therapy will treat small bowel bacterial overgrowth. So we have seen different entities like tropical sprue, celiac disease, Crohn's disease, short bowel syndrome, bacterial overgrowth syndrome. So like this. Okay, so to summarize, we have seen the digestion and absorption of nutrients. So thank you all.